Quantum theory heavily relies on the concept of operators. An operator is an instruction that does something to a function and gives another function as a result. Formally, let's take a function f of x and operate on it with operator a. We often put a hat on an operator symbol to indicate it's an operator. The result of a operating on f is another function. Let's call it g of x. Here's an example. Let's assume f of x is cosine of x, and the operator is the first derivative, d dx. Then a operating on f of x equals d dx cosine x, which of course is minus sine of x. Another example. Take f of x equal 3 times x to the fifth, and the operator a being the second derivative this time, d dx squared. A operating on f will be d squared dx squared operating on 3x to the fifth. And if we take the one derivative at a time, we get d dx of 15x to the fourth, and that is equal to 60 times x to the third. This is the basic mechanism how operators work. Typical operators in quantum theory are the multiplication, differentiation, as we have seen above, and integration. Operator notation does not introduce any new math. It just provides a shorthand notation for math you already know. A special class of operators are linear operators. They satisfy the two following general properties. A linear operator a operating on a sum of two functions is equal to the sum of the two separate results of a operating on f and on g separately. Also, a operating on a constant times a function is equal to the constant times a operating on a function. We basically can pull the constant out of the operators. In quantum theory, we deal exclusively with linear operators. Nonlinear operators are more complicated. And a few examples include the square root, the square, or the logarithm. Here are some basic properties of operators. The sum of two operators should be understood like this. A plus b operating on f is equal to a operating on f plus b operating on f. The combination of two operators, a, b, f, is supposed to mean that b operates on f first, giving a result which is then operated on with a. The nth power of an operator indicates n successive applications of the operator. For example, if you have a to the fourth operating on f, it's equal to a operating on f. Lastly, an exponential operator, e to the power of a, can be understood in terms of its power series expansion. It's equal to 1 plus a squared over 2 factorial plus a cubed over 3 factorial, and so on. This expression can be applied utilizing the previous property of the exponentiation, the summation, and the successive operations. Again, in summary, operators are nothing new. They're just a new shorthand for some old math.